alaikum wa rahmatullahi wa barakatuh. My name is Hanan, and today I will be presenting this session about signal convolution in discrete time and in continuous time. Please feel free to contact me if you have any questions. I'm open for suggestions and corrections. And this is our lesson plan. So let us start by convolution in LTI systems. First, we must recall the unit impulse signal, its definition. This is the normalization condition for the unit impulse signal, and this is the shifting and sampling behavior of the unit impulse signal, which is basically that whenever a function f of t is multiplied by the shifted unit impulse signal, it forces the function to be evaluated at the shift value, which is t naught. And this is also the same sampling behavior. These two equations are almost identical. And next, let us look at convolution in LTI systems. So convolution can tell us how an LTI system would respond to an input. So if the input to an LTI system is delta t, the output will be ht. Okay, ht is known as the impulse response. And if we know ht, if we know ht, we can pretty much know the output of this system to any input signal. So for example, if the input signal is x of t, the output is going to be y of t, and y of t is going to be x of t convolved with the impulse response h of t. And this is possible for two reasons. First, because the system is LTI, linear time invariant, and secondly, because x of t itself can be represented as a sum of shifted and weighted unit impulses. So we can see this from this approximation or this decomposition integral. For example, if the input to the LTI system was was only this term, which is a delta t minus t negative 1, then the output is going to be a shifted and weighted impulse response. So the output is going to be t minus 1. And if we enter this term separately, so if this term is our input, then our output is going to be bh t minus t naught. And then if we input x of t as a whole, as a sum of all of these, then we can expect the output yt to be a sum of shifted and weighted impulse responses. So it's going to be aht minus t negative 1 plus bh t minus t naught plus ch t minus t1, and so on. So these are the properties of convolution. It's associative, distributive, and commutative, and they make solving problems easier, especially if, for example, when the systems that are in cascade. We will see later in an example. These are the formulas for computing the convolution in discrete time and continuous time. This equation here is used to find the length of the output signal y of n in discrete time. So this is the length of the input signal, and this is the length of the impulse response. And we can also determine from h of t, from the impulse response, we can also determine if the system is causal and stable. If a system is causal, if h of t is less than 0 for h of t is less than 0, h of t is equal to 0 for t less than 0, and a system is stable if this integral gives a finite value. So let's do the first example on convolution properties. Let's do letter A first. We can see from figure 217b that xt is equal to yt xt convolved with ht. This is number one. Number two, we can see that this one here, this yt, is also wt convolved with h2t. And then we can see that wt itself is xt convolved with h1t. And then if we substitute this here, we get that yt is equal to xt convolved with h1t. This is wt convolved with h2t. And then we use the associativity property. Then we can say that xt convolved with h1t convolved with h2t, which means if we compare it, I know this is very easy, if we compare it to the first equation here, then this portion must be ht. So we need to find ht. So let's just use the convolution integral. So it's going to be h1 tau h2 t minus tau d tau exponent negative 2 tau u tau times 2 exponent negative t minus tau u t minus tau d tau. So let's find the limits. These are the restricting functions. So we have u tau is equal to 1 for tau greater than or equal to 0, and it's 0 otherwise. And this is ut minus tau is equal to 1 for tau less than or equal to t, and for tau greater than t it's 0. So the upper limit must be tau, and the upper limit must be t, and the lower limit must be 0. Then we can get rid of the ut's, and then we can just add the exponents. Negative 2 tau minus t plus tau is equal to minus tau minus t. So 0 to exponent tau plus t d tau, which is equal to minus 2. And then we substitute the limits. So we get minus 2 exponent negative 2t minus exponent negative t. And this is only valid between 0 and t. So we can say that it's for t greater than or equal to 0. Or we can also say minus 2 exponent negative 2t minus exponent minus t times ut. And let's rewrite it 2 exponent negative t minus exponent negative 2t to ut. So this is the result, and this is ht. Okay, so let's do letter B. So letter B asks us to determine if the overall system is stable, so we just need to integrate this impulse response under the absolute value dt. So since we have ut, we can just change the limits to be from 0 to infinity. Exponent negative t minus exponent negative 2t dt. And then we can integrate each term separately. Take out the 2, 0 to infinity, exponent negative t dt minus 0 to infinity, exponent minus 2t dt. 2, we can minus 1, and then 0 minus 1 minus 1 over negative 2. This should be in a bracket. And then 0 minus 1, close the bracket. So 2, 1 minus half. So 1 minus half is half, and half times 2 is 1, which is less than infinity. So it's stable. And let's do an example in continuous time. So compute yt is equal to xt convolved with ht. So compute yt. Again, we use the convolution integral, minus infinity to infinity. Minus infinity to infinity, x of tau h t minus tau d tau. So let's substitute first, then we can see what we can do about the limits. So we can straight away expand. So it's going to be u tau minus 3 exponent negative 3 t minus tau u t minus tau, that's the first term. And the second term will be d tau, will be minus negative to 0 u tau minus 5 exponent minus 3 t minus tau ut minus tau. And then let's do the limits again in the same way. So the first one, the limits will be tau less than or equal to t, and this would be tau greater than or equal to 3. So from 3 to t, and then exponent negative 3 t minus tau d tau minus, we do the same thing here. This is tau greater than or equal to 5, and this is tau less than or equal to t. 5 to t, exponent negative 3 tau d tau. So it's the same integral, but we just have different limits. Okay, and let's not forget in limits فده is valid only between 3 and t. يعني this integral and this integral is only valid from 5 and t. So we need to add the unit step functions. So all of this is multiplied with u t minus 3, and this is u t minus 5, ut minus 3, ut minus 5. Okay, so this is the result. We can also write it in the other form, in the overlap form. So we have for t less than 3, and then for t between 3 and less than 5, and then for t greater than 5. The first range, there's no overlap, it's 0, because the first one starts at t equal 3. So for t less than 3, there's no overlap. And then for the range between 3 and 5, we have this term. So the value is going to be 1/3, 1 minus exponent negative 3, t minus 3. And then for t greater than 5, we will have a combination of these two terms. Let's also try to sketch them. Next question, compute gt. Let's find the derivative of xt. So dxt dt is equal to, where is xt? So this is xt, ut minus 3 minus ut minus 5. So derivative hypothetical unit impulse signal, t minus 3 minus delta t minus 5. Then we compute gt. So we convolve this. So actually we want to do minus 3 convolve minus t minus 5 convolved with ht. So we use the distributive property. So it's gonna be delta t minus 3 convolved with ht minus delta t minus 5 convolved with ht. And then from here we can use the shifting property of the unit impulse signal. So the shifting property is that ht convolved with delta t minus t naught is equal to ht minus t naught. So we can just straight away say that the result with g of t will be equal to ht minus 3 minus ht minus 5. So this is gt. So how is gt related to yt? So if we compare them, we can see that there are some common terms, but they have opposite signs, and there's also a factor of 1/3. For example, this term is the same as this term, but there's a 1/3 and the signs are opposite. So let's try to find the derivative of yt. So dyt dt is equal to 0 minus negative 3 exponent negative 3 t minus 3 times ut minus 3. That's the first one. 1 minus exponent negative 3 t minus 3 times delta t minus 3. And the next term, the same way, negative 3 exponent t minus 5 ut minus 5 plus 1 minus exponent negative 3 t minus 5. So now we can use this property, the shifting property, or the sampling property, which means that for this term, we substitute t equal 3, and for this term, we substitute here t equal 5. So we get 0 for both of them, and they cancel. So the result will be equal to, so we get exponent minus 3, t minus 3, ut minus 3, minus exponent negative 3, t minus 5, ut minus 5, and this is equal to gt. So to relate x of t, to relate g of t to y of t, to relate g of t to y of t, we can say that, or actually what we found, that d y of t dt is equal to g of t. And then we also found that g of t is the derivative of x of t alone convolved with h of t. And then in part A, we found that y of t is equal to x of t convolved with h of t. So we can substitute this here. So we get the derivative of x of t convolved with h of t. So the derivative of the entire convolution is equal to g of t, which is equal to the derivative of x of t alone dt with ht. So this is a property of LTI systems, firstly, and secondly, the relationship between gt to yt. This is the relationship. So this is the last example, which is convolution in discrete time. So let us try to do first letter A. We will try to do A by the convolution sum, and B using the graphical method. So we start by writing down the equation for the convolution sum. So S1n will be equal to the summation minus infinity to infinity of xn z n minus k, or xk, or summation from minus infinity to infinity zk xn minus k. So we can use whichever, but in this case we can fix any of the signals, either z or x, but if we fix x, our range will be, if we fix the signal x, our range is going to be, or k is going to be from minus 2 to 2 in the summation, and if we fix z, our range is going to be from 0 to 3, but from 0 to 3. But we can see that xn or xk later actually has all amplitudes as 1, so it will be easier to multiply out. So let us do by fixing xk. So it's going to be the summation from minus 2 to 2 z. We said we will fix x, so it's going to be xk z n minus k. Next, we use the length formula to find the length of the output signal. So the length of S1 is going to be the length of x plus the length of z minus 1. So the length of x is equal to 1, 2, 3, 4, 5. So this is 5, and 1, 2, 3, 4. This has 4. So it's 5 plus 4 minus 1, which is equal to 8. And then we need to find the start and ending index of the n. So the starting index will be the start at L, the start at x, and the start at z. So x starts from minus 2 and z starts from 0. So it's negative 2 plus 0 minus 2. And then the ending index, we can see that x ends at 2 and z ends at 0, 1, 2, 3, ends at 3. So 2 plus 3, 5. So n is between minus 2 to 5. So let us expand our summation first, and then we can start to substitute n values one by one. So it's going to be x minus 2 z n plus 2 plus x minus 1 z. I'm just substituting the k values here in this summation. Z n minus n plus 1 plus x 0 z n plus x 1 z n minus 1 plus x2 times z n minus 2. And now we can substitute these values, and all of them are equal to 1. So this is the equation after we simplified it, after we simplified the summation, and now we can start substituting the values of n in this range. So we start S1 at n equal negative 2. This is going to be z0 plus z minus 1 plus z minus 2, z minus 3, z minus 4. So we find these values. So z0 is equal to 1, and all of these are 0. So this is the only number. And then we substitute minus 1, so we get z 1 plus z 0 plus z negative 1 plus z minus 2 plus z minus 3, and all of these from this term onwards are going to evaluate to 0. So we only have z1 and z0, so that's 1 plus 1 is equal to 2. And we do the same thing for 0 and 1 and 2 all the way up to s1 5. Since this is a repetitive process, I'm just going to put the solution in the slide. And now we can move on to letter B. Go to letter B, where we have to find s to n. So first thing we find the length of the output signal. So it's going to be ly plus lf, ly plus lf minus 1. So the length of y, 5, plus the length of f, equal to 5 minus 1 is 9. And then we again find the starting and ending indexes. And start, this one, minus 1 minus 2. So it's going to be minus 2 plus, and this one starts at 0 minus 1 minus 2, so minus 2 minus 2 minus 4, and it ends at, this one ends at 0 1 2, and this one ends at 0 1 also 2, so 2 plus 2 4, so the end range is from minus 4 to 4. And now that we found the starting and ending indexes, remember that in the convolution sum the equation looks like this. We have to flip one of the signals, so it's yk fn minus k, or summation yn minus k fk. So let's choose one signal to flip, either y or f. Let's flip y. Let's just reverse it in time, that's all. Minus 1 and minus 2 and 1 and 2. And next we write the n in a table, the n ranges. So we know that our n is from minus 4 to 4, so minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 2, 3, and 4. And then this is f minus n, by the way. And then let's put our fixed signal. So where is our fixed signal? It's yn, and let's just put it as it is. So we only write the amplitudes, okay? So we have 1 1 minus 1 minus 1 minus 1. These are the amplitudes. And then for this one we have, okay, so for the f negative n, we are going to shift it. This is the signal that we are going to shift to the right. So the first time it's going to be shifted by minus 4, because our n starts at minus 4, which means that this point here is going to be at minus 4. So only this portion is going to appear. So this is the position of the new 0, and the amplitude at 0 is 0. So we put the amplitude at 0, and then we put this amplitude, and then followed by this amplitude. So minus 1 minus 2, minus 1 minus 2. And this is the signal that we're going to shift to the right every time. So from the first line here, we will get the value at n equal negative 4. And then n equal minus 3, n equal minus 2, n equal minus 1. In every row, we're going to shift the signal to the right. So again, after we shift at n equal minus 3, this 0 is going to come here. So 0, and then minus 1, minus 2. And now the amplitude at minus 4 is going to be this minus 1. So 0, minus 1, minus 2, minus 1, and the amplitude here is 2. And then we just continue shifting to the right. Minus 1, minus 2, minus 1, positive 2, 2, negative 1, 0, negative 1, negative 2. Do not get confused by the rows. So I will do the rest. I will pause the video and continue. Next, we are only going to consider the regions that have an overlap for the multiplication. So the first one is going to be S1 at n equal -4. And the only region where there's an overlap is here, -2 times 1. So it's going to be equal to -2 times 1. S1 at -3, the overlap is going to be here. So it's going to be this times this. Wait. This times this plus this times this. So it's going to be -1 times 1 plus -2 times 1. The next one is going to be S1 at -2. So this is the first overlap, this is the second, and this is the third. So S1 at -2 will be equal to 0 times 1, -1 times 1, -2 times -1, and so on. Sorry, it's actually S2. My bad. So S2 -1, the overlap is going to be -1. So this column, this row, I mean, you know, and this one. So I think I will also just leave the answers because it's a repetitive process. آخر حاجة, let us try to do letter C. Letter C, it's very simple. So دي عبارة عن S2N, S3N is going to be S2N, this is C, S2N convolved with 2 del N plus 1. So عارفين إنه من shifting property we can just use it, فهتبقى 2 S2 N plus 1. So هنجيب S2N هنعمل لها shifting, والshifting factor هنا عندنا N plus 1 هيكون N minus -1. So the shifting factor يعني زي T not قبل. So whatever was at 0, whatever amplitude was at 0 will now be at -1. So خلينا نجيب الانسر بتاع S2N. طيب ده بالنسبة ل S2N. So whatever was at 0 دي كانت 0 حقها هيبقى ده هيكون هيبقى -1. إذا ده بقى -1 معناته 0 الجديد هنا، فعشان يبقى S2N plus 1. So كده نحن عملنا البورشن ده بس. Now we need to multiply all of the amplitudes by 2 to get the final result. So هتبقى -4 -6 2 4 8 8 -2 -2 -4. Okay, that's all. Okay, yeah, that's all, and thank you for watching. Bye.